Remote sensing is the term given to any technique which allows measurements to be taken at a remote location without any physical sensors being located there. Many techniques are used, with more being developed, but the main ones we will discuss are radar, atmospherics, and satellite imagery. Firstly, let's take a closer look at how radar images are produced, how we should interpret them and use them to our advantage. Any type of radar works on the basic principle of a transmitter sending a pulsed beam of electromagnetic radiation and a receiver to record any reflected signals. Weather radar are specifically designed to detect precipitation. However, there are two different types. The basic and more common weather radar detect the location and extent of the precipitation and its intensity, whereas the newer Doppler radar also detects the lateral motion of precipitation particles. The time elapsed between the broadcast of the signal and the arrival of the return signal is directly related to the distance between the precipitation and the radar unit. The reflectivity, or the amount of power reflected back to the unit, provides information about the precipitation intensity. The type of precipitation can also be estimated from the reflectivity. As a rough guide, the heavier the rain, the stronger the returning signal. The rainfall radar picture usually comprises various colours, representing differing rainfall intensities, with a map overlaid for reference. Here, blue represents light rain, with the brighter reds and yellows heavier rain. It is very easy to look at a radar picture and interpret areas of precipitation and movement. However, it can be difficult to tell the difference between an echo that's precipitation and an echo that's not. The most common return from the radar is reflection from the ground. But since the ground is a stationary object, it's relatively simple to eliminate these ground echoes from the radar picture. However, precipitation may be falling in the shadow of some high ground, which cannot be seen by the radar. Another effect which regularly occurs is something called anomalous propagation, shortened to anaprop. As the beam of radiation passes through the atmosphere, it curves downwards. This is caused by the vertical variation in density of the atmosphere. It travels faster where the density is less. In extreme cases, the air near the ground may be so cold and dense that a radar beam which starts out moving upward is bent all the way down to the ground. The same can also be observed where there is a strong static stability in the lower atmosphere. The diagram shows a typical structure, with a strong temperature inversion and marked hydrolapse in the lower few thousand feet. Within the inversion layer, the radar beam is refracted downwards relative to its initial path. The result of both of these effects is an increase in ground clutter on the radar image, shown here. This will normally occur during anticyclonic conditions, or where there is a relatively deep nocturnal inversion from the surface. On this example, we can see ground return caused by hills. If you have data from more than one radar, anaprop is easy to identify, because the neighbouring radars generally won't see the same thing. Also, by comparing the radar image with surface observations, and perhaps satellite pictures, you can tell if rainfall should be expected in that area, therefore eliminating any anaprop. Sometimes interference from other radiation sources can produce errors. A good example of this can be the sun. If the radar happens to point directly towards sunrise or sunset, the reflectivity pattern can feature a ray of strong echo extending from the radar toward the sun. In this example, the spike to the west-southwest is caused by interference from another transmitter. In some areas, local wildlife can sometimes create strange and unexpected radar returns, for instance, flocking birds and insect swarms. It's usual to see a radar composite or mosaic image covering a larger area. Each radar will have a coverage of around 100 to 150 kilometers, so by piecing several together we can see the bigger picture. Often these will be in a movie loop, so we can determine development, speed and direction of movement of weather. Next, let's take a look at a form of remote sensing called atmospherics. This is a technique used to identify areas of lightning and hence thunderstorm activity. As we've heard many times throughout this training course, thunderstorm activity poses a serious hazard to aviation, not only from lightning strikes, but also from associated phenomena: severe icing, severe turbulence, wind shear, and heavy precipitation, often hail. So being able to remotely identify areas of thunderstorm activity in data-sparse regions means we can identify areas which are best to avoid flying into. This tool also allows forecasters to give early warning to individual airfields, or ATC, as to the arrival of an approaching thunderstorm. The most commonly used system is called ATD, which stands for Arrival Time Difference. It was realized in the early 1920s that when a lightning flash occurs, radio waves are emitted over a wide frequency band, often called atmospherics, or simply spherics. You can quite often hear this as interference when listening to your radio. An ATD system calculates the location of remote lightning flash from the time difference of the atmospheric arriving at various pairs of detector stations. The origin of the lightning can then be calculated. Obviously, this involves precise measurements of time, and the system will use an atomic clock to synchronize all detection stations. The ATD system used by the Met Office in the UK is fully automated, and recent developments mean that lightning can be located at a rate of 8,000 flashes per hour and to a much higher degree of accuracy than ever before. This is a satellite picture of South America, with the ATD lightning data overlaid. Even halfway round the world, the system is accurate to within a few kilometers. From the calculations, a map showing lightning strikes can be produced. These maps are usually animated in steps through time to show the developments and movement of thunderstorm activity, normally updated every 5 minutes.